Hello there, Dr. Tishan here, and in this video I'd like to take a look at an analytic representation of limits. I'd like to preface this video by letting you know that I did previously make an introductory graphic representation of limits video that you may want to take a look at in case this topic is brand new to you. We start studying limits in a calculus class, so you may want to look at the introduction and the graphic representation before we get to the analytic. So let's just recall when we're working on finding limits of functions, okay? When we're finding limits of functions, well, you're going to take a look and x values are going to approach a certain number, and we're going to use numbers here, not infinities. So as the x's approach a certain number, your limit, we're just going to figure out where the y values are going. That's all we're doing. As the x's approach a certain number from the left and from the right, we want to see where the y's are going. If the left and the right are going the same place, then you have a limit. And you never have to get to that number. You just have to approach from the left and from the right, see where it's going. So when you're evaluating limits analytically, you don't have a graph, you don't have a table, just you have a function, an algebraic function, and you want to figure out where the y's are going, you don't know what it looks like. All right, well, we're going to use the direct substitution principle. The first thing you do if you see a limit problem, you're going to use the direct substitution principle. The direct substitution principle, just all it does is it tells you to take your c value, take the number, and you just substitute it right into the function. You substituted it in. And when you take this number here and you substitute it into the function, what's going to happen? You're going to get one of these three outcomes, okay? So one of these three outcomes. So if you get a real number, if you take your c value, substitute it into the function, and you get a real number, no zeros in the denominator, you get a real number, then that's your answer. You're done. Simple. All right, and that's all you have to do with the, if it works out to be a real number, okay? If you take your c value and you substitute it into the function and you end up with a 0 in the denominator, okay? So 0 in the denominator, okay, well then we've got some work to do. This video, we're going to look at 0 over 0 form, the factor and cancel method, okay? So 0 in the denominator, as you can see here, comes in two different forms, okay? Comes in 0 over 0, which is indeterminate form, or you have non-zero over 0, which is undefined, and that's for a future video, that's going to give you an infinite limit, okay? So 0 over 0, indeterminate form, non-zero over 0, undefined. These two situations with 0 in the denominator are handled very differently. So just before we actually do the calculus of this, let's do a brief algebraic review or numeric review with the 0 in the denominator. So let's make sure we understand what which situation is which, okay? So when I'm reviewing this, usually I start with something we all can do, okay, with or without a calculator. 15 divided by 3. What is 15 divided by 3? 15 divided by 3 is 5. 15 divided by 3 is 5. That's just a basic division problem. How can we check our answer? Well, to check our answer, you can take the quotient and you can multiply the quotient by the divisor, you get the dividend. 5 times 3 is 15. It all checks out, and that's how we do our multiplication division. All right, now let's put some zeros in here and see what happens when we've got some zeros involved. What about 0 divided by 3, okay? So 0 divided by 3 is 0. We don't have 0 in the denominator, it's in the numerator, but notice that it all checks out. When you take 0 and multiply it by 3, you get 0, and so everything checks out and we're fine, okay? All right, now what happens if we switch that around and put the 3 up top in the numerator and then 0 in the denominator? Now what's going to happen, okay? Think about it. What number can I multiply by 0 and get 3, okay? Nothing works. There are no solutions to this. Nothing works, okay? So there's no solutions here. Okay, nothing works in this situation, okay? So nothing works at all. So non-zero over 0, we say that this is, we call this undefined. All right, so this is undefined, okay? So now what about if we have 0 divided by 0, okay? What about 0 divided by 0? If I take 0 and divide by 0, what do I get, okay? Well, let's look at it this way. Look at it this way. What number can you multiply 0 and get 0? What number? Can you take 3 and multiply 3 times 0 is 0? 3 works, okay? It works, okay? What if I took 5? Okay, is 5 times 0 equal to 0? Sure, 5 works. That works, okay? Anything, I mean, what if I take, I don't know, number 8? Okay, number 8. 8 times 0 is 0. It works. 8 works, okay? You can do whatever you want to try, okay? You want to try -2? What is -2 times 0? 0, and it works, okay? You can try an irrational number. Want to put a pi in there? What is pi times 0, okay? Pi times 0 is 0, and it works also, okay? So what are we dealing with here? Okay, here we have infinitely many solutions. Okay, infinitely many solutions for this situation. So this situation, 0 divided by 0, this is called indeterminate form. This is called indeterminate form. Okay, so the point being is that when you have 0 divided by 0, infinitely many solutions, non-zero divided by 0, no solutions, okay? Non-zero divided by 0, this is your undefined because you don't have any solutions. 0 divided by 0, you have infinitely many solutions in determinate form. You can see how so different these two situations are. Non-zero over 0 versus 0 over 0, such different situations. So when you get to advanced math classes, you have a 0 in the denominator. These two situations are going to be handled very differently as you're working through. So in this video, we're going to take a look at a couple of examples of the 0 over 0 situation, okay? So we're going to look algebraically at the 0 over 0. And so for our first example, all right, so for our first example, let's take a look right here as x approaches 2, okay? We're going to take the x squared minus 2x, all right, over x squared plus x minus 6. Okay, so we're going to look at this as our first example for this for today. All right, so we want to evaluate this limit. We don't have a graph to look at. We don't have a table to use. All we have is what it says right here. Okay, so we want to evaluate this limit. So what do we do first? Okay, what we do first, we're going to use our direct substitution. Follow the flow chart. Okay, so the flow chart, you have a limit problem you want to solve analytically. What do we do first? Substitution, direct substitution principle. We're going to take the number 2, substitute it in. Okay, so somewhere off to the side, substitute the 2 in. So you're going to end up with 2 squared minus 2 times 2 in the numerator, because you're going to substitute 2 in for x, so 2 squared minus 2 times 2, and then in the denominator, we're going to take 2 squared plus 2, and then minus 6, and let's evaluate this, okay? So 2 squared in the numerator, all right, so what do we end up with here? We're going to end up with 4 minus 4 in the numerator, okay? The denominator, 2 squared is 4 plus 2 minus 6 in the denominator, okay? In the numerator, 4 minus 4, that is 0. In the denominator, 4 plus 2, 6, and 6 minus 6 is 0 in the denominator. So the first thing we're doing is we're going to use our direct substitution principle to see what we have, okay? Now, if we did not have a 0 in the denominator, if we had a real number, then that's our answer and we're done. It's direct substitution, we're done. All right, what if we have 0 over 0? Okay, so 0 over 0, we're going to have a limit, but we're going to have to do something to change the form of our algebraic expression so we can compute what the limit is, okay? So, but we will have a limit, okay? And we'll look at a graph of this as soon as we're done with the computation. All right, so we're going to use, so what can we do? Well, because we have indeterminate form, remember that generated infinitely many solutions, we have to take the function and do something algebraic to change its form. We have options, okay, factor and cancel. If there are radicals involved, you can multiply by conjugate. If it's a complex fraction, you can simplify it. If there's grouping, algebraic groupings, you can expand and multiply it out. And if all these techniques fail, you can always go back and resort to a graph, try to work that out, or a table. So we're going to probably do a video on each of these topics. We're going to concentrate on factor and cancel here. The numerator, the denominator are both factorable, so we're going to factor and cancel. So let's take the limit as x approaches 2. Okay, so in the numerator, what can we do to factor the numerator? It's a binomial, 2 terms, so you can see that each of these 2 terms, we've got an x in common that you can pull out the x, okay? So when you take an x out of the first term, x squared, you're going to have an x left over, and then the 2x here, when you take the x out, you have the 2 left over. Okay, so here the numerator completely factored. All right, now what about the denominator, right? So the denominator is actually going to be, it's a trinomial, so we want to factor the trinomial. So x squared, well, so x times x is x squared, and we want to just look for, if the trial and error method, look for 2 numbers whose product is a -6. The product is a -6, but the sum has to be what? The coefficient on the x of +1, okay? So when you think about combinations of numbers with 1s and 6, 2s and 3s, which ones give us a product of -6 and a sum of +1? That would be a +3 times a -2. Okay, so there's your x squared, and then 3x's take away 2x's, give you 1x, there's your -6, okay? Now, notice there's a common factor, and x minus 2 is a common factor, and so we can cancel those. It's factor and cancel, okay? So we can cancel those out, all right? We want to move those out of the way, okay? Now, what if you use your factor and cancel method and nothing cancels, okay? Well, if you have 0 over 0, then you check your algebra, because you're going to be able to factor and cancel. You got to get the 0 over 0 out of there, okay? Something is causing the 0 over 0, and this is what it is, the x minus 2 factor, because you take the 2 and plug it in, 2 minus 2, 2 minus 2, there's your 0 over 0 that you're moving out there, all right? So we're going to move that outside, and so now we have the limit. X is approaching 2. We have an x left over in the numerator, x minus 2's cancel, and we have the x plus 3 in the denominator. Okay, so now that we took our 0 over 0 and we changed the form of the function, okay, now we do direct substitute again to our new simplified version of the function, all right? So now take the 2 and substitute it in for x, okay? Take the 2 and substitute it in for x, all right? As soon as you make that substitution, you don't write the limit expression down anymore. And then we simplify this, and so you have a 2 in the numerator, you have a 5 in the denominator. So as the x's approach 2 on this function from the left and the right, looks like the y's are going to 2/5. All right, so it looks like the y's are going to 2/5. Okay, all right, and you can check this. You can check and see, you know, if you were to grab a graphing calculator and graph this, okay, so whatever this might look like, if you were to graph a, all right, so x equals -3 is probably going to be a vertical asymptote, okay? So if you were to graph this on a graphing calculator, okay, what would the graph look like? Probably looks something like this on the left side of this. And then over here on the right side, it's probably going to look something along the lines here, okay? So as you can see, and from the previous video when we looked at graphic representation of limits, all right, as the x's are approaching 2 from the left and from the right, the y values on the y-axis appear to be going to, well, 2/5 is what we computed, okay? So that's what it is, limits of a function. You don't ever have to get to x equals 2, but as this function approaches from the left and from the right, as you're approaching 2 from the left and from the right, limits are, you're trying to figure out where the y values, where the function values are going, okay? So here's the first example. All right, and well, the second example is on the back of this board, so just a quick review so you can remember what we're doing, because this information is not on the back. So limits, we're going to take the c value and plug it into the function, all right? You just take the number and you plug it in, direct substitution principle, and you just want to see what happens. One of these 3 situations off the flow chart is going to happen. You're either going to get no zeros in the denominator, a real number, no zeros in the denominator. If that happens, you are done. That's your answer, okay? Or you are going to get a 0 in the denominator. Remember, zeros in the denominator come in 2 different forms, okay? All right, 0 over 0, indeterminate form, infinitely many solutions. And so when you have 0 over 0, you need to take the function and do something algebraic, trig, whatever it is. You need to do something to change the form of this function, okay? So this video, we're going to concentrate on factor and cancel, and then I'll visit some of the other topics in future videos, okay? Let's take a look at example number 2. We have 2 examples, so let's take a look at example number 2. Okay, so here we go with example number 2. All right, We want to take the limit as x approaches 3 of, well, we've got a cubic in the numerator. Can you see it? X cubed minus 3x squared plus 5x minus 15. We've got a quadratic in the denominator, 4x squared minus 11x minus 3. Let's take a look at this, okay? So how do we evaluate limits? Very first thing you do analytically when you're evaluating limits is we take this C value, this number here, 3, and we're going to substitute it in. Okay, so we're going to take the 3, we're going to substitute it in. So what is that going to give us? I'm just going to work this off to the side. So it's going to give us 3 cubed minus 3 times 3 squared. So minus 3 times 3 squared, okay, plus 5 times 3. All right, so plus 5 times 3, and then minus 15. This is where we're at in the numerator, okay? We're going to take the 3, plug it into the denominator. It gives us 4 times 3 squared, okay? Minus 11 times 3, okay? So minus 11 times 3 minus 3. All right, so just off to the side, we're just going to substitute and compute this, okay? 3 cubed is 27, all right, so that's 27. 3 squared, 9 times 3, that's 27, okay? 5 times 3 is 15, and minus 15, this is what your numerator gives you expanded out. What about the denominator? 3 squared, you have to evaluate the exponents before you multiply, order of operations. So 3 squared, 9 times 4, that's 36, okay? Minus 11 times 3 is 33, minus 3. Okay, numerator 27 minus 27 is 0, plus 15 minus 15 is 0. We've got a 0 in the numerator. Okay, what about the denominator? 36 minus 33 is 3. 3 minus 3 is 0. We've got 0 over 0. Okay, so we have 0 over 0 here as well. Okay, off to the side. And this can be mental math. You don't have to see what your professors want you to do, but this mental math you want to see, because if you ended up with a real number, that's your answer. Okay, zero's in the denominator though. Now this is 0 over 0, so we have indeterminate form. Indeterminate form means we've got to take the function, change its form. We are going to have an answer. We're going to have a real number for a limit for this problem. The hole in the graph. When you have 0 over 0 with these algebraic functions, then it is a hole in the graph is what's happening. X equals 3 is a hole in the graph, so we know the left and the right are going someplace, okay? The direct substitution's not finding it for us, so we have to go ahead and we're going to factor and cancel. So how do we factor this? This is a little bit more involved. So how would we factor here? So we want to take the limit, x approaches 3. How would we even begin to factor this? Okay, the numerator, you have a cubic function in the numerator. Okay, so one of the what you can do with the numerator is we can consider factor by grouping. If you remember that from your algebra class. So factor by grouping, we're going to break this into 2 groups. We're going to take this first group, this second group. We're going to break this up. The 4 terms, we're going to take these first 2 terms, second 2 terms. When you use factor by grouping, you want to make sure that your algebraic expression is in descending order by power. So to the third, to the second, to the first, to the 0. So let's look at the first group. What can we pull out of the first group of 2 terms? What can we factor out? Okay, we can factor out an x squared. So you take an x squared out of the first group, what's left over? Take out an x squared from x to the 3rd power, there's an x left over here. Take the x squared out of this term and you have 3. All right, and then let's take a look at the second group, 5x minus 15. What can we factor out of our second group? You can factor out a 5, right? So take a 5 out of the first group here, take 5, so you have a 5x, you're going to factor out the 5, there's an x left over. Now be careful here, 15, so when you divide out the 5 from the 15, you have a 3 left over, okay? So there is the beginning stage of factor by grouping. We'll have to go another step, but we're on our way to it, okay? Now the denominator, okay, so the denominator is a trinomial. How would we factor this, okay? This is a little bit of a different strategy because you don't have a 1 as a leading coefficient on your quadratic. You have a 4, okay? So now how can we get 4x squared? Do we want 4x times 1x, or do we want 2x times 2x, okay? So instead of trial and error, because I know this is a lot to think about, All right, this is where you want to start to learn, especially, you know, if you're working on time tests, you want to learn how to work smarter and not harder here. Okay, think through, strategize. All right, looking at our numerator, do you see x minus 3? X minus 3 is a factor in each of these two terms, okay? We're using the factor and cancel method because this is indeterminate form. So we're going to be able to factor and cancel. We need one of these factors to be the same as what's in the numerator. So, you know, x minus 3 is probably going to be one of my factors here. Okay, so you don't have to think too hard. So now what is my other factor going to be? Well, x times what is 4x squared? I must need a 4x here, okay? And then negative 3 for the last term. Well, negative 3 times what will give me negative 3? Well, negative 3 times a positive 1. So it looks like this is what I've got for my denominator, 4x squared, okay? And then negative 12x plus 1x is a negative 11x, and then there's your negative 3. So denominator is completely factored. Now we got to finish up with the numerator, but just use these strategies so you don't have to think so hard when you're doing the algebraic breakdown. All right, so now what do we got? We've got the limit as x approaches 3. We still need to finish our factor by grouping, okay? So factor by grouping in this numerator, what do we have here? We still have these two groups, correct? So look at these two groups. What do these two groups have in common? They have the x minus 3 in common. So you're going to factor out the x minus 3. When you take the x minus 3 out of this term, there's your x squared, okay? And when you take the x minus 3 out of this term, there's your positive 5. Okay, so here's your numerator completely factored by grouping. Your denominator, you've got 4x plus 1, and we've got x minus 3. All right, so we've completely factored the numerator, we've completely factored the denominator. Do you see any common factors that cancel? Yes, you always will, because 0 over 0. So if you have indeterminate form, you have an algebraic fraction, and it's factor and cancel method, you will be able to cancel out these common factors. As a removable discontinuity, you'll be able to cancel those out. Okay, so what do we have left over now? So we're going to take the limit, keep carrying this down because we haven't substituted in again yet. Limit as x goes to 3. Well, the numerator, we have x squared plus 5 left over. Okay, the denominator, we have 4x plus 1. Okay, because the x minus 3 is canceled. All right. Now that we've completely simplified our algebraic fraction with the cubic and the quadratic, let's go ahead and compute this limit. To take the 3 and substitute it in. Okay, so you have 3 squared plus 5 in the numerator. The denominator is going to give us 4 times 3 plus 1. Okay, and so let's go ahead and compute 3 squared is 9. And 9 plus 5 is 14, okay? And then 4 times 3 in the denominator is 12. All right, and 12 plus 1 is 13. And so here is our answer, okay? So our answer is 14 over 13, okay? What does this mean? This means whatever this algebraic graph looks like, you can check it on, if you have the graphing calculator, type this into your y equals, whatever this is going to look like, this algebraic fraction, okay, as the x's approach 3, positive 3 from the left and the right, the y's are going down 14/3, a little bit over 1, okay? So it just tells you where the y's are going. As the x's approach from the left and the right, it tells you where the y values are going, okay? So hopefully this will help you get started with your analytic representation of limits. Remember, I have a graphic representation video out there also, and I'll have more. I'm going to rationalization technique and complex fraction and expanding, and so there's plenty of other techniques, and I'm just going to do one in each video. So thank you so much for your attention. Thank you for watching. I hope this helps with all of your endeavors out there. Take care. Thank you.